Hello, everybody, and today we're going to talk about the chi-square distribution. This video will be all about the chi-square, and it'll be the test for fit, the goodness of fit. You see in front of you the chi-square test of independence. Well, the chi-square test of fit is very similar. There's slight differences between the chi-square test of fit and test of independence. Just because there's such a small difference, that's why I'm going to focus on today the chi-square test of fit. What do I mean by that? Well, let's just jump into examples to show you. What we have here in our first example is the DMV has stated the above percent when it comes to age of drivers in general. The DMV states that 16% of drivers are under the age of 20, 56% of the drivers are 30 and older, and between the two groups is 28%. So we don't know if we believe that. So we perform a quick study and we find that 68 in our study, 68 kids under the age of 20 are driving. 92 are between the age of 20 and 29. And age 30 and older, there's 140 people driving. So the question is, given this data that we've collected, do we believe this is truly the DMV statistics? Do we believe in the DMV in their breakdown of drivers? So how do we test this? Well, this is called a chi-square. Can't write. Chi-square. We'll try this one more time. Chi-square test of fit. And so how does one run a chi-square test of fit? Well, what one does is you start out with your hypotheses, right? Your stage one, your H naught. So H naught is always what we assume. And until somebody otherwise shows me, I got to believe the DMV stats are fair, are accurate. Whatever you want to say, are fair, are accurate. H1, if I can come up with a data set that otherwise speaks to it, then I'm going to say my alternative is the DMV stats are not accurate. They have to be updated. Okay, that's very, very reasonable. 3 years, data could change. So how does one test that? Well, that test statistic I showed in the very beginning on the formula sheet is what I'm going to use. It's called the chi-square statistic. I'm going to calculate out this test statistic and compare it to whatever level of significance that is given in the question. I didn't give a level of significance. I'll state it that it's going to be 5%, though we can change it to see what other conclusions happen if we change it. So what do we have here? We have the null and alternative hypothesis. The next thing you typically do is you come up with the test statistic. So what is the test statistic? It showed you. I showed you in the formula sheet. Hopefully you paused the video. If not, rewind the video, pause it, and have that formula in mind. You have this F naught and you have this FE. Well, F naught are the observed values above. F naught are the observed values in a particular order so you can keep track of them. 68, 92, and 140. And you should be cognizant of the order you wrote it down. I wrote in order that you see above, that is under 20, between 20 and 30, and 30 and above. It's very important you keep track of your categories. So what do we have here? Now, what's expected? Well, expected is based on the percents the DMV gives you. First thing I need to figure out is I need to figure out total. Because I need to know how many people we did survey. It did not say that in the question, but with a quick sum, you can find out we sampled 300 people. It did not say that in the opening paragraph here, so I had to check that out. Why do I need that number? Because if I believe in the DMV statement, I'm going to assume that I believed the DMV statement, then 16% of the people I studied should be under the age of 20. The math for that would be 16%, right? 16% of 300. So I would expect 48 people. We got 68, we expected 48. Is that too far apart? And that, my friends, is the basis of the formula for the chi-square to fit. We'll get to that in a second. First, I'm calculating out FE, the expected frequencies. That's what FE stands for, the expected frequencies. Well, again, there are 300 people in your survey. I expect 28% of them if I believe in the DMV stats. So 84 of them. Well, that's pretty close. All right, but again, how do we compare them? We're going to need a statistic. This is how you build the statistic. You need all these numbers. Last but not least, you have 300 people in your survey, and according to my data above, 56% are going to be from the bracket of 30 and older. So there is my breakdown. And you can notice when you sum these up, once again, you get 300. So what you get is the observed versus what's expected based on the statistics given to you. Now what do? You compare them. How do we compare them? According to that formula. The formula of comparison was, F naught minus FE and squared. That makes sense in many respects. To be a comparison is to take the original minus the expected. That makes sense. You square it, for if you don't square it, you get these positive and negatives to cancel out, and you get this number that really doesn't mean anything. But unfortunately, because you squared it, you've now put it into square units. So we need to define this in some respects, this variable in some respects in the same units that we're doing, the counts here. Because if we don't, we now have square counts. And because we have square counts, we're an issue. And that's why it was decided we divide by FE. This counts again. That means we have square counts over counts, which gives us back a count when I talk about units. And that's how this formula was developed. So let's write it in. Let's slowly write it in, and I would pause the video, try it yourself, and then, or pause the video after I've written the code and check it out. What is it? It's F naught minus FE, obviously, squared, divided by FE. And that's it. And I'll put it back up in the box here so you can pause and see that and check it out. And now that I've written it, I'm just going to copy and paste it down. And according to the formula, the sum of, and I got to be careful, I put it in the wrong spot. I want to sum this right here. According to the formula for the statistic, if you do this formula and sum it up over every optional pair, which would be in this case, there's 3 of them. If you sum it up over each category, if you want to say it that way, if you sum it up over each category, then you will, in fact, have the statistic. And there it is. My test statistic is 13.76. Now, that might seem large. And yes, if we were doing the Z or T distribution, I would automatically reject. But we are dealing with the chi-squared distribution. The chi-squared distribution is heavily shifted to the right. So a 13.76 doesn't naturally mean I'm going to reject. Again, you should look up pictures of the chi-squared distribution and see that the shape, the skewness to the right. And based on degrees of freedom, it could be more or less skewed. And that's, again, left for readers to take a look at the pictures. So I've done my step 1, laid down my null and alternative. Step 2. I came up with my chi-square statistic. There it is. Step 3, I need a critical region. I need a critical region. Well, a critical region, you would draw the picture and put a bar down. That bar, though, you need to know the degrees of freedom to draw the chi-square distribution accurately. To draw the critical region accurately, you need to know degrees of freedom. That really tells me about the picture. Well, the good news, degrees of freedom will always be number of groups minus 1. All right, it'll be the number of groups, so groups minus 1. In this case, we have 3 groups we're comparing, so 3 minus 1, not March 1st, so equals 3 minus 1, i.e., yes, I know. Unfortunately now, this is a common mistake. If you put it into a format that's a date, it'll stay in there until you go back to number or general and change it back to a number. So now it's back to a number. That happens a lot in Excel. If you put in any type of thing that looks like a date, it'll change the date. So you got to go back and format the cell back to general or number, your choice. And so there's the degrees of freedom. I want to make that clear. For a chi-square distribution, for fit, you would look at the number of groups you have you're comparing and then do minus 1 for the bias. Excellent. From here, I can do the chi-inverse. If you've watched many of my videos, you notice critical regions are always built by the inverse function. If this is a normal, I do the norm S inverse. If this is a T, I do the T inverse. Because we're dealing with the chi distribution, and I guess I wrote it wrong, they've changed it, the chi-squared dot inverse. That's the one I want. I was looking at an older version right there. But this chi-squared dot inverse, okay, is asking for probability. That's a darn good question. I'm going to state that probability is lined up with this box right here. And we'll talk about that in a second. Comma, degrees of freedom, which is this box. Now, it's not going to give me a number because it doesn't understand box C33. See, box C33 is where I'll put my alpha. And I got to be careful. It's not really my alpha. Your alpha we'll put here. If your alpha is 5%, your level of significance is 5%, then the area under the chi-squared critical value would be 1 minus that number. And what that means is, again, think about your shape, your chi-squared distribution, heavily skewed to the right. We have one bar in that picture. And in fact, it behoove me if I drew that picture real quickly for you guys. So what do we have here? We have a chi-squared which is degrees of freedom of 2. That picture is, if you excuse my penmanship, looks roughly like that. That's roughly what a chi-squared degrees of freedom of 2 looks like. So what we do now is we put this bar down in the sand. And if you get far enough up, we are going to reject H naught. If you don't get far enough, you DNR. You do not reject H naught. So it all depends on which side you're on. Did you get far enough across the bar? So the question is, where is this bar? Well, somebody gives me the rejection level. That's called the level of significance, 5%. I made it up. I said 5%. And so since I know the rejection level is 5%, that means the area below is 95% in my picture. Because if the area above is 5%, then the area below must be 95%. It has to add up to 100% because it's a probability mass function. So what we have here is 5% of, 95% below. Chi-squared inverse, just like the rest of the inverse, if you want to know where the bar is, you need to tell me the area below. You tell me the area below 95%. Oh, by the way, tell me what curve this is. It's degrees of freedom of 2. Then I could do the calculus on it, and that's what Excel does very well. Excel says, hey, you tell me your degrees of freedom. Sorry, you tell me the curve, that is the bar, and you tell me the degrees of freedom so I can tell you the curve. Degrees of freedom is right here, D30. And because alpha was 5%, then the area underneath would be 95, and so then that would be my cutoff. So I now can, in step 4, make my conclusion, because I'm ready to make my conclusion. I notice that the test statistic is what? It's that number. So the test statistic is that number. I notice my cutoff, or critical value, if you want to call it that, is right there. My test statistic clearly is over the cutoff. The test stat is greater than the cutoff. That tells me I must reject H naught. In bottom line, you should always put it back in a sentence that makes sense. All right, what is the sentence that makes sense? Bottom line, I believe the DMV stats are not accurate, and further investigation is needed. I notice up here I said stats and it says states now, so I'm going to change that. I notice this says stats states, and it should say stats, and of course that says DMY. Don't know what that is. Should be DMV. All right, good. Now that my hypotheses are written correctly, and this is the 4-step process for doing a critical region rejection on a chi-squared test of fit. You state the no. As far as I can tell, the stats look accurate until you show me there's enough evidence that they're not accurate. So how do we test that? Well, in this situation, we have a known probability breakdown versus what we got. And that's clearly a chi-square test of fit. When you're looking at a probability breakdown and the statistics you collected, to compare them, you do a chi-square test of fit. And what you do is you take your values versus what's expected. And you create the statistic to measure that out. And you get a 1376. That 1376 is well over the critical cutoff value of 599. Now, some would say, well, yeah, so you rejected at 5%. Would you reject at 1%? That's a totally separate question, all right? A part B. Would you reject at 1%? Well, I can easily change this to 1%, 0.01. Once things are automated, now you can change it pretty quick. Alpha is 1%, means the area below is 99%, means my cutoff is 9.21. Well, yes. You wanted a 5% level? Guess what? I can give you a 1% level. My statistic is so statistically significant that I actually go past the 1% level. So I can reject not only at 5%, but I can reject H0 at 1% LOS. So I even have a more thorough test here. Yes, I passed the 5%. If that's all you wanted, yes, I passed the 5% level of significance. But I changed it to 1% and I still passed that critical cutoff value. This was the cutoff, 9.21, pretty far out there. But my statistic was farther than that, and that's why I'm rejecting. And what does it mean to reject? It means I don't believe the data from the DMV is accurate. Now, can I go dig a little further? Yes. That's why I like this table. Sometimes this table is not there, but this is why I like this table. These numbers add up to 1376, my statistic. Please notice this is more than half of your statistical value, right? If you actually look at this number, 8.33, it almost beats a 1% level of significance on its own, right? And 8.33 almost beats 921, the cutoff on its own. That means this comparison right here is what's very unusual in the data. I think the DMV's representation of the drivers under 20 age is what's really off. The other ones are okay, but this one, that's 20 people off. They only expected 48 drivers. I got 68 drivers. That's a big difference according to my sample. And that's why, again, I'm looking at this and going, yep, my test clearly is pointing to the DMV might want to do a larger study and look at their statistics, or at least just update the website. This could be an easy answer. The DMV did not update their website. I mean, where did I get this information from? If I got it from the DMV's website, all I can say is, guys, update your website, please. Your data is no longer accurate. Cool. By the way, some people ask about checks, and there's nothing wrong with checks. The checks are all about the FE, what's expected. If the values you see that are expected are all above 5, then you pass your check. We really want the number of expected to be above 5. This is really a quick little check that we have to ensure accuracy when it comes to the test. So just a quick scan, my expecteds are all above 5, and so that means that I have a good test. Some people also look at the observed, by the way. If the observed are all above 5, that is value 5, these are all above 5, which means, again, we should have an accurate result. That is our assumption, is that each one of these should be above 5. If too many of these are below 5, we may have an insufficient sample size. That's really what it comes down to, is an insufficient sample size. But because all these numbers are greater than 5, we know we have a sufficient sample size, and so these results are accurate. That would be our check if you wanted to run the check on the chi-square goodness of fit. All right, guys, I'm going to pause the video. You guys are going to now try example 2 and see how you do. All right, guys, I'm back. So, honestly, once you have written one of these right correctly, you save it. And then you just utilize it and do it again. That's really what it comes down to. First, you got to understand you are doing a chi-square test of fit, though. Let's check this out. So what do we have? we have a dice, and we believe that an employee at the casino has put a loaded dice into the game. We decide to check this theory and investigate this die. So, when we're the pit bosses, we come in there, grab the die, and we're going to check it out for ourselves. So we run a simulation. So these are the numbers on the die, 1 through 6. And this is when we roll the dice, this is what we got for their frequency when we roll the dice. So, all right, here we go. Number 1. Let's kind of follow through the steps. H naught. What was our hypothesis? Well, we're going to assume the die is fair. I'm going to assume the employee didn't rig the game. So I'm going to assume that. But my H1 is if I get enough evidence, then the die is biased. And that means this employee has a lot of explaining to do to me in the casino. So now that we have that out of the way, we do the test stat. That's really, it's wash and repeat the steps. We need the F0, we need the FE, and we need the formula. So the F0, that is the observed values. The F naught are the observed values. So we observed a 40, a 35, a 33, a 30, a 33, and a 29. Let me make sure I wrote those numbers right. 40, 35, 33, 30, 33, 29. So this would be a simulation. All right, you tested the dice and you rolled the dice, and this is what happened. So overall, let me do a sum here because I'd like to know how many times did I actually roll that dice. How many times did I actually roll the dice? The answer is 200 times. So we rolled the dice 200 times, and this was the breakdown. Got it. So what was the expected breakdown? Well, this one's going to be easier to deal with because this is if it's a fair dice, what's expected is the same number every time. That is 1/6 of 200 every single darn time. It is a 6-sided dice. So 1 out of 6 times, you should see the number 1. 1 out of 6 times, you should see the number 2. So we should see a nice uniform distribution right across. Add that up, and as a check, yep, it's still 200. The question is, are any of these far enough apart for me to go, whoa, there's clearly something wrong with this dice? The question is, how far apart can they be? This is what I observed when I rolled the dice. This is what expected if the dice was fair. Well, that's why the formula was built. Again, the most obvious thing is, yes, you would subtract the 2. The problem, if you subtract the 2, every now and then you get a negative, and that messes with the calculations. So the most obvious thing you do when you're doing negatives is you square it. The problem is you squared the units. Now we're in square counts. You can't utilize square counts, so we're going to offset the square by dividing by the event again, and that brings it back to normal count, normal units. And so we do this for each one of the observations, and then we add it up. And this is my test statistic. So my test statistic is a 232. Is that enough to reject? The answer is, I don't know. This is not a Z or T. If it was a Z or T, there's a chance. But this is a chi-square distribution. And remember our picture. A chi-square distribution is skewed to the right. Now, this picture changes based on degrees of freedom, okay? This is not the exact same chi-squared curve. I want you to warn that. I'm looking at this picture, but it's going to be a different chi-squared curve that you'd have to look up the picture of if you want to know what it looks like. To know how to draw the picture, I need the degrees of freedom. The degrees of freedom will tell me how to draw the picture. But I want to go on the steps I've utilized before. So step 3, the critical region. Well, the good news, critical region does involve the degrees of freedom. So in this case, we had 6 groups, 6 sides of the dice. So it would be 6 minus 1 would be the answer. Oh, I did this mistake again. It would be 6 minus 1, which means we have a degrees of freedom of 5. Again, it's groups minus 1 is your degrees of freedom. All right, now we're going to run down the chi dot inverse. We're going to run down the alpha, and we're going to run down the area under. So we have the chi inverse, the chi, and again, chi-square dot inverse to be accurate. The probability will be here once I write it in, comma, degrees of freedom is up here. I like automating my function in Excel, so once I've done it right, I'm good for no matter what alphas I choose. And that's what I'm doing here is, all right, my alpha, I didn't give it to you. But let's say somebody said, this is a very critical thing. Let's really bring all the evidence. 1% level significance. That means a type 1 error has a very thin chance of happening. Okay? Remember, this is your type 1 error probability. And so if you're really worried about a type 1 error, okay, rejection when you shouldn't, that's what a type 1 error is, rejecting when you shouldn't, then you really want to limit the chances of type 1 error. So with that, in fact, 1 minus would be the area underneath, which is 99%, and there's your cutoff. Clearly, my number doesn't come close to the cutoff, and that means I'm not rejecting. So again, step 4, right, my conclusion, let me put it in the right way, my conclusion, what do we have here? Well, we have the test, the stat. That's easy to see. The test stat I got was a 232. My cutoff, in this case, was a whopping 15. In this case, my test stat is less than my cutoff, and that tells me I will not reject. I do not reject H not at 1% LOS. What does that mean? Bottom line, there is no evidence the die is biased. That's what we have. We have no evidence the die is biased. As far as I can tell, let the employee go back to work. He is not cheating, or she. So the die, and of course, there are some spelling mistakes. That happens. The math is good, people. Spelling mistakes happen. I do apologize for that. So what we did? This is what is known as a chi-square test of fit. What happens is, again, you have a typical breakdown, and then you collect a sample because you're not sure if you believe that typical breakdown. Especially in games, you might want to know if something's fair or not fair. And so what we have here is a check on that. And we get a statistic. After we get a statistic, we need something to compare it to. And so to compare it to, I need the degrees of freedom to draw the appropriate chi-squared picture. And also, it's not about drawing the picture, it's about doing the calculus. The calculus, all right, to do the integral, the advanced calculus, I need to know the degrees of freedom. Once I have the degrees of freedom, that picks the right curve. I'm going to find the area underneath. Second, I need to know the area underneath. Well, if the rejection region, according to my picture, the rejection region is your alpha, it's a 1% level, then if this is 1%, then what's underneath is 99%. All right, that's the idea, is there's going to be a bar in the sand. If we collect enough evidence, we're going to reject the null. If we don't collect enough evidence, like in this example, we did not collect enough evidence, we do not reject. Everything looks good. And that's what's going on here. And the cool thing is, somebody said, well, okay, what if we loosen the strains a little bit? What if we go down to 5%? Well, let's go down to 5%. Yes, the bar gets lower, but not lower than the 232 as our test statistic. So once again, we would not reject at a 5% level. What if we want to bring our type 1 error up higher? I don't know why you'd want to do that, but let's say you wouldn't type it there. I just made the formula useless. Use your back arrow to change that. Let's say we brought it down to 10%, an alpha of 10%. Bring the bar even lower. So this is the lowest bar I'd look at, which is a 10% level of significance. All right? A 10% level of significance means there's a 10% chance I made a type 1 error. That means I rejected and I should not have. But in this case, I'm not rejecting, right? In this case, I do not reject. So there's a chance I've made a type 2 error here. But I'll leave that for you to investigate. My job in this video is to make sure you guys could create a chi-square test for fitness. All right, guys, thank you for watching this video. Stay tuned for the chi-squared independence test.